Well, hello everyone. The question for the night is talk about which one of these subparts or sets listed in the following parts are subspaces of R cube. And yeah, we'll do this fairly quickly. This will take a while though, because we're going through four rather long examples and I'll be working through them in detail. I expect you to at least know what the definition of a subspace is. You can look that up on the internet. However, I'll quickly guide you to how to check if something is a subspace of another space. So if we had to check a set of vectors, say, uh, so no, let's just set of vectors, not just a vector. So capital V is a subspace of W. Well, then if a set of vectors V is a subspace of W, you must ensure that the zero vector must belong to V. Um, and you must also ensure it must also then belong to W, of course. You must also check if v1 a vector and another vector both are elements of V, given that v1 and v2 are both vectors from V. So this is basically saying the sum of it, the operation of addition is closed under this, and the last one is for some C that is real, that is a scalar, and v1 again, which is an element of V. I'll explain this in more detail as we proceed with the examples, because that is sort of the way we usually operate. Right on. Sorry, I guess I should just do this here. So let's go through part A. So part A gives us set A capital A, which is lambda plus mu cube lambda minus mu cube, where lambda and mu are both real numbers. Now clearly, for lambda is equal to 0 and mu is equal to 0, we get a vector 0, 0, which is clearly an element, and therefore the first test passes. Let's do the second test. So you have lambda 1, vector lambda 1 plus mu 1 cube, lambda 1 minus mu 1 cube. So I've assumed a particular vector, that's why I've taken concrete values for lambda and mu. Lambda 1, mu 1. This is a particular element. And I'll assume another one, lambda 2, lambda 2. This is usually how you must do this. You must just assume specific examples and show that such a thing is or isn't possible. Now if we add these vectors, we'll get something like lambda 1 plus lambda 2, lambda 1 plus mu 1 cube, plus lambda 2 plus mu 2 cube, lambda 1 plus lambda 2 minus mu 1 cube minus mu 2 cube. Right, so this goes here, and then let's rearrange everything for the sake of convenience. Mu 1 cube plus mu 2 cube So this is the summed vector for this one and this one. These are obviously both assumed to be elements from V. And we have to show that these are elements in R cube basically. That's why we use 0, 0, 0, because 0, 0, 0 are elements of R cube. Now, if we assume, so since this is a real number and this is a real number, their summation must also be real number. So let that be lambda cube, just assuming lambda cube. Now this is, since this is a real number, this is a real number, can we say that this is mu 1 cube plus mu 2 cube root, whole cubed, and we can say something like lambda 3 minus cube root of mu 1 cube plus mu 2 cube, whole cube. We can say this because, my bad, yes, we can say this because if mu1 and mu2 are elements of R, the real number set, then mu1 cube and mu2 cube must also be elements, since if a number is a real number, its cube is also a real number, so 2 cubed is 8, still a real number. The summation will still be a real number, right? And their cube root will also be a real number. So we can be assured that whatever this number is, right here, it's still very much within the real number set. And therefore, we can assume another third concrete value mu3, which is the cube root of mu1 cube plus mu2 cube. And since we can assume concrete values, this means that this just resolves to something like lambda 3 plus mu cube lambda cube minus, sorry, mu cube, sorry, mu 3 cube. And since lambda 3 and mu 3 are still values, this means this is still very much within the vector space of R cube. Sorry, we're supposed to prove this for R cube. And so we have also proved the second property, since these are all real numbers. The third property is to check for scalars. So we again assume a concrete one. So lambda 1 plus mu 1 cube, lambda 1 minus mu 1 cube. And what we do is multiply it by scalar c. C is obviously some real number. And what we'll get is c lambda 1 plus c mu 1 cube, c lambda 1 minus c mu 1 cube. This is the vector once multiplied. And the thing with this is, this can be assumed to be lambda 2, because if lambda 1 is a real number such as 3.5, it multiplied with another real number such as pi would still be pi 3.5, another real number. So we can again say this is lambda 2 because we assumed c1 lambda 1 to be lambda 2. We can rewrite this as something like c mu 1 cube root whole to the power cube, and then this is lambda 2 again minus cube root of c mu 1 cube whole cube. Again, these are real numbers, and we must now just say this is a real number. This is a real number. Why? Because c mu 1 cube is a real number, since mu 1 is a real number. If mu 1 is a real number, then mu 1 cube is a real number. Then c mu 1 cube is a real number, since this is cube, this is a real number, and multiplication of real number set is closed. And then the cube root of this must also be a real number, since the domain and range of the cube root function third radical is again real number set to real number set. And so we can say that this can be rewritten as something like lambda 2 plus say mu 2 cube and lambda 2 minus mu 2 cube, where mu 2 is equal to 3c mu 1 cube. This is again an element of the third real number set, and therefore this is, since we've satisfied property 1, 2 and 3, this is a subspace. Sorry, A is a subspace of R cube. This was a lot of work, obviously, and this is what we'll be doing for all of them. If it wasn't clear, just bear with me. Let's do another example. Yeah, it will maybe become more clear. So B is the set lambda square minus lambda square 0, such that lambda is a real number. Obviously, the first condition satisfied, as when lambda is equal to 0, the vector just becomes 0, 0, 0, 0. And this is obviously the 0 vector, and therefore you can say the 0 vector is an element of R cube. So this is satisfied. You can look at the second one. Again, you assume two concrete values. You sum these, and then that becomes lambda 1 squared, lambda 2 squared. Sorry, and we take this on the next step, and again, if lambda 1 and lambda 2 are real numbers, then lambda 1 square is a real number, lambda 2 square is a real number, and that sum must also be a real number. And therefore, this is still a real number, and this is still a real number. That will now say is lambda 3. So, if we say that, also this square shouldn't be outside, I'm so sorry. Perhaps what I should do is get rid of this for now and put a square here. So if you take this, you can say that this is the same as, some lambda 3 minus some lambda 3 is 0. And you need to find squares, right? So the thing is, you can always assume that lambda 1. Okay, so instead, let's assume this to be root, so that this is square as well. So you can rewrite this as sort of lambda 1 square plus lambda 2 square root, and then the whole thing squared. I know it's an indirect way of doing things, but if you assume this, you can show that it is being squared. So that would show that this is lambda 3 squared, lambda 3 squared. They're quite simple. And this is again an element of R cube. So this is done. And now the last one. Oh, sorry, shouldn't have drawn the line. Part 3 is you have C lambda. So you try to multiply. So you assume again, concrete example. So you have lambda square minus lambda square 0. You try to multiply C inside this. So C lambda square minus C lambda square 0. Now the thing is, you can't actually do anything here, because if you assume C lambda square is some other lambda dash, so you could say something like lambda dash is equal to square root of C lambda square, so that lambda dash square is C lambda square, and so this would become lambda dash. But then this no longer works because you don't know how to figure out this, as the second C is positive. Negative C lambda square is no longer solvable, as lambda square is always positive, anything squared is positive, and multiplying it by a negative number ahead only makes this unsolvable. So if you assume a positive C greater than 0, then this will no longer work. If you assume a C less than 0, then this works and this no longer works. So this just never works. Like, there is no value you can assume for C where multiplying it inside to lambda square minus lambda square still gives you a subspace. And so since 1, 2 pass but 3 fails, you can say B is not a subspace of R cube. It's the notation, that's what you're wondering. Right, so that's part B. And now let's move on to part C. I have that written somewhere here. Just assume that gamma is a real number. Okay. And then show that C is G1, G2, G3, which is a real number thing, and G1 minus 2, G2 plus 3, G3 is gamma, and they're all related to each other like this. Okay, so let's try to show the first property. So if gamma is equal to 0, then it implies that you can find G1 some value. An example can be 0. G2 again some value. G3 again some value. All of them, if by example, are 0, then this thing produces 0, and so this produces 0. And if there's 0, 0, 0, this means that 0 vector is an element of C. And so you're done. You've shown that 1 actually passes in this case. Let's show part 2. So that's trying to sum this. So I'll assume 2 vectors this time, G1, G2, G3. Yes. and I'll try to add this to g1 dash, g2 dash, g3 dash. If we add these together, we get something fairly simple and expected. Oh, yep. Right. And let's see if this still satisfies the relation given to us. So that is, so the thing is, here when we did this, we sort of implied that two equations were true. G1 minus 2 G2 plus 3 Z3 for some gamma. And we sort of implied that G1 dash minus 2 G2 dash plus G3 dash were true for some other gamma. Let's see if this sort of still holds, all of this is still true. So for this, the equation will look like G1 G2, sorry, G1 G1 dash minus 2 G2 G2 dash plus 3 G3 is equal to sum. We assume. Let's show that our assumption is actually valid. So if G1 is some real number, G2 is a real number, then this entire thing is a real number. If this is a real number, this is a real number, this again is a real number. This is a real number, this is a real number, then the sum is again a real number. Same argument follows. And so this is actually possible. You can find such values for some gamma dash dash. So this is different from this gamma, this gamma, this gamma. And so this is actually possible. You can find an addition like so. Right. So let's go to part 3. And part 3, we try to multiply the scalar. So again, we assume a concrete solution G1, G2, G3, and we multiply it by C, dot product with C. That is CG1, CG2, CG3. In this case, it was implied that G1 minus 2G2 plus 3G3 was some gamma. That was a real number. In this case, it's sort of, let's see if this will still hold true. CG1 minus 2 CG2 plus C ZC3 is some gamma dash. And yes, this is true because if G1 and G2 and G3 are real numbers, then them multiplied with another constant will still be a real number because multiplication, the real number set is closed. And so you can actually still find such a vector and always create such a vector for any given C. So this is valid. So you can still say that 1, 2, and 3 are true, and therefore C is a subspace of R cube. However, gamma must be 0 for condition 1 to be satisfied. So this is not true for all of them. It's just that if you choose gamma to be true, which is what we chose here, then this can be shown to be the case. Because if gamma is not 0, then G1, G2, G3, at least one of them must have a non-zero value. And that's not possible because we have to show that the zero vector is an element. So all three of them must have zero values. So this is immediately a contradiction. So the only way that part 3 is satisfied is on a subcondition of this. So when the question asks, is it true for all real numbers? No. However, it's true for this subcase where gamma is equal to 0. So you have to be careful about how you answer the question. Oh, this is 0, right? Right, let's move on to the last part. And this is part D. So this looks like this: G1, G2, G3, where G2 is so G1, G3 are still all real numbers. They haven't given us that, but I think we can assume that's a reasonable assumption given the previous part. And G2 is now, instead of that, an integer. So let's show if 0. So clearly 0 vector is an element of D, as 0, G1, G2, G3 are all allowed. 0 is a real number. It's also an integer. It's again a real number. So this works. This was condition 1. My bad. Now let's show that this is also true for say condition 2. In condition 2, we have G1. We again assume a concrete solution G3. And is this it? Yeah. And we assume another one G1 dash, G2 dash, G3 dash. Right. So if we sum this up, we get G1 plus G1 dash, G2 plus G2 dash, G3 plus G3 dash. If this is a real number, this is a real number, then the whole thing is a real number. So this is okay. If this is a real number, this is a real number, the whole thing is again a real number. If this is an integer and this is an integer, the whole thing is an integer. So this is still okay. The example of this could be like if you add 2 and 3, it still gives you 5. If you add 610 minus 300, it still gives you 310. You can take whatever integer you want and you can add them together. You'll always get an integer. So you can say that the operation of addition is always closed under the set of integers. And so this works. So it is still closed. This is still working. It's all good. We can now look at 3. And 3 is multiplying it with C, sorry, dot product with C. And if you get CG1, CG2, CG3, this works for a few of these. So this is a real number, this is a real number, so their multiplication is a real number. This is a real number, this is a real number, so their multiplication is a real number. This is a natural number, sorry, an integer, and this is a real number. And so their product can be a real number as well. An example that I found on the internet is if you get C to be pi, then which is a real number. If you multiply a constant inside, then this becomes pi G2. Now if G2 is say just 1, an integer, then this becomes 3.14 something, and that clearly is not an element. And therefore it fails on this. And so you can say since 3 fails, D is not a subspace of R cube. And this is really all you need to know. This is how to, we've done quite some work here. I hope this was good. But yeah, this is how you go on showing if something is a subspace of something else. Yep, thank you.